Welcome everyone to the last talk in this year's GHC track of the ZeroHack Social Distancing Edition. For those who didn't join the previous talks, you can raise questions and discuss on the GHC-track-discussion channel and have a voice chat afterwards in the GHC-voice channel. In this talk, we'll keep the question to the end. Without further ado, it's my pleasure to introduce Nicolas Frisby for this talk. Take it away.
Thank you, Andreas. This talk is about typechecker plugins. I'm going to try to demystify them a little bit, if anybody has always been curious. My name is Nicolas Frisby. You can see my two personal and work emails. I'm also at Tweak. So I've got a related project at this year's ZeroHack, which I've been neglecting a little bit to finish my slides. Sorry about that. But the general question is trying to document what it is that GHC expects from a typechecker plugin. There's some documentation on the wiki, but it's sort of just enough for sort of an expert ticket going. So we'd like to expand that a little bit so it's more welcoming. So we have the TC plugins channel on Discord, and then I created that GitHub repo just to sort of accumulate whatever we come up with this weekend. So please feel free to stop on by if this piques your interest, or if you feel like you could contribute, that'd be excellent. For this particular talk, I'm going to talk about sort of two pieces. Basically, GHC has these expectations about what a plugin should do, and it follows the sort of Pareto 80-20 shape where in the timeline where you've written a completely capable plugin, 20% of your effort will have gotten you 80% of your features. Like a little bit of work gets you a long way, but then to really finish it off, it requires a lot more understanding because there's a lot of corner cases that don't come up in most GHC programs, but do come up in some. And you'd like your plugin to eventually support those. So I'm going to discuss sort of the very basics to how to get started with a plugin. And then I'll also discuss a little bit of the concepts that you'll only need to know when you are starting, when you start trying to finish your plugin off and make it do the last, make it as capable as possible. So you'll get a long ways with just the first bit of information, but eventually you will need the second piece of information. So I'll talk about this two parts because I don't, this is my first ZeroHack. I really didn't know what to expect. So I wanted to aim for the beginners, but also include a little bit of advanced stuff. So the talking points for this talk, basically when you sit down to write a plugin, you will be faced with this type. These are not the real types, but they're a little simplified for the slides. But you're given a bunch of CTs, whatever those are. There's a monad you're going to work in, and you either report a contradiction or you report some changes to those CTs. So first, you have to figure out what these data types are. So generally, we're going to be talking about what this signature means and what GHC expects from this function that you will be providing. So the talking points are this notion of simple and implication constraint, and the implication tree, which is going to be the basic concept that helps you understand why GHC is invoking your plugin the way it's invoking your plugin. And then we'll talk about the different flavors of constraints. I won't actually get into the constraints actual structure because that requires a lot more background. It wouldn't fit in 30 minutes. But these 4 flavors of constraints are a good place to start. And then those different flavors interact in different ways, and that's what this matrix is. And from that matrix, I can suggest a basic organization for your plugin. So that's the general shape of where we're headed. I will very briefly try to motivate plugins in case no one's ever looked into this, or someone hasn't ever looked into this in the audience. So the classic motivation is you know something about the types that GHC apparently doesn't know. And I think the known nat and the natural addition is sort of, as soon as you interact with those types a little bit, you'll realize that GHC has very limited capability when it comes to understanding addition of known nats, or of nats and the known nat constraints. So this is sort of the first place where a lot of people obviously know that addition is commutative, whereas GHC just seems to be oblivious to that fact. So plugins, so there are plugins that handle this. Right? With the plugin, GHC will be able to solve known nat x plus y from known nat y plus x. But the sort of question I'm interested at the moment is why doesn't GHC already know that? GHC does have some knowledge about naturals, but it doesn't include commutativity. So my conjecture is sort of fourfold here. The base reason is that the people who could make it understand are preoccupied with something else. Why does it require experts? It's because formal methods is hard, right? The GHC constraint solver is part of the type checker, and that's obviously a sophisticated piece of machinery. But for something like addition of naturals, like there's prior art in the literature for the past 70 or whatever years about how to do that in a formal way. And that's where the third bullet point comes in, I think, which is really my main message, is you not only have to know how to reason about naturals, you have to know about how to reason about naturals in a way that is compatible with the GHC constraint solver that you are extending. That's the tricky part, because the GHC constraint solver is sophisticated and you can't step on its toes, and you have to understand what it can do for you and what it needs you to do for it. So that's why it's really hard, is to take whatever existing art you have about the domain you want to teach GHC about and integrate it into what GHC already does. And then lastly, it's just sort of how all project management goes. Most GHC programs get by with what GHC can already do for naturals. I'm sure there's lots more that would benefit from more sophisticated naturals, like maybe some sort of strongly typed vector library that has lengths in the types. I've written a couple of those and they're awkward because it doesn't know about commutativity when you append vectors, things like that. But the main message here is that plugins are, it's sort of the sharp edges. It's a pretty raw part of the GHC compiler interface, but they're really cool when you get them to work. So I don't want to discourage you, but I do want to warn you that it's not a well-trod path. Okay, so I've moved from centering my slides to leftmost to indicate that we are now into the technical content. So the first off, I want to say we talk about type checker plugins, but that's a bit of a misnomer. The type checker is a big thing, but we're really the plugin only affects a part of it, the constraint solver. So the type checker plugin right now, at least, is really a constraint solver plugin. There are other plugins in GHC which can be like source plugins or core plugins, and those are different ends of the pipeline. But right now, the only part of the type checker we can affect is the constraint solver. And then even constraint solver itself is a bit of a misnomer. It's more of a constraint simplifier. And the only really subtlety there is that you don't have to solve all the constraints. If you can't solve them all, that's not necessarily a type error. So that's just me being nitpicky. But I will go with constraint solver from here on because that's what everybody says when they talk about it. So the constraint solver is a part of the type checker because the type checker follows what's sort of called the French school, which I think is from Didier Remy. I don't really know. I think that might have been before my time. But you break a sophisticated type checker into two parts. One where you traverse the program and you're finding how different expressions interact, and based on that, you generate some constraints. Some of those will be so easy you can discharge them immediately. Like if int must equal int, then you can discharge that in place. But there will be more sophisticated ones, perhaps ones that rely on unification or a constraint solver. And so you just accumulate those until some incremental points, maybe when you leave the scope of a let-bound function definition. And then once you do that, that's when you invoke the constraint solver on that set of constraints to see if it can simplify them, see how they interact, maybe solve them all, or generate type errors if there's contradictions. So that's the piece of the type checker that type checker plugins currently affect. So we'll talk about that because you have to interact with it pretty intimately. So the constraint solver is conceptually a loop. It's a loop and it just works with a set of whatever constraints are currently relevant or have accumulated so far and you're trying to solve. And as you solve them, the constraints that will change because you're simplifying the constraints. So at some point in the loop, hopefully there's no more constraints, in which case you're done, you've solved them all. But if there are more constraints, then GHC will attempt to use its built-in rules, which I'll discuss in a bit. If any of those built-in rules fire, then essentially this conceptual loop starts over again. So it's slowly making progress. But eventually the built-in rules will be done. The constraints will be sort of fully processed by the built-in rules. And then GHC gives your plugins a chance to make changes. If your plugin finds something that it thinks is relevant and makes a change, then the whole loop will start again. So if your plugin makes a change, then that might trigger another change that the built-in rules can proceed with, etc. So the built-in rules and the plugins interact in this sort of loop until eventually both of them say, there's nothing more I can do with those constraints. And then the loop is over. Either there were no more constraints, so the loop's done, or there were some constraints, and depending on the source program, that's either a type error or just whatever remaining constraints end up being the inferred context on some function definition that we were type checking. So this whole concept comes from the architecture of the constraint solver the architecture of the constraint solver is referred to as this outside-in X algorithm, which is from a amazing but long paper from the Journal of Functional Programming in 2016. there's lots of great information in there, and it explains the basic concepts, but it also defines the default X. X here is the constraint domain. It's the domains that the solver is going to be able to handle. And GHC has one built in. That's what I call the built-in rules. And this is the default X. And it does what every Haskell programmer sort of understands it must do, which is it handles type classes and type families. So unfortunately, a type plugin author ultimately, maybe not. Maybe there'll be some plugins that are so simple that they can't risk doing this. But particularly if your plugin does anything about equalities, like, for example, reasoning that x plus y should be equal to y plus x, right? That's an equality that you're interacting with. So when you're interacting with equalities, there's a good chance that you're going to interfere with GHC's own solver and what it does on equalities. So this is like a warning that you need to understand the built-in rules, at least to some extent, to at least make sure you don't interfere with them. So if you always flip x equals y to y equals x and GHC always flips it back, then you're just going to be an infinite loop. And GHC has sort of a limit on how long it'll go, but it'll just fail. You'll always fail to type check a module because of that. So I'm going to talk a little about, in this talk, basically how the constraint solver works. So this is that type signature for a plugin. And at least at this point, we know now what the list of CTs is. Right? That's the list of constraints that we're currently working on in this particular invocation of the solver. And we've reached a point where the built-in rules are done with those CTs. There's a technical term where they are inert with respect to the built-in rules. And then now your plugin has a chance to make either find a contradiction or maybe make some changes to those CTs. But what is a CT? So I'm going to talk about just general constraints, and I'll work my way towards discussing what CTs are handed to your plugin. The basic idea for that, and this is relevant to the outside-in algorithm, is this so-called implication tree. So there are two kinds of constraints. There are simple constraints, which are the ones we think of daily, just type class applications and equivalences. And then there's implication constraints, which are these, anything where it's an implication, right? If I have OR, then I also have searchable or something like that. Until recently, these were not available in Surface Haskell, but they've always been inside of the compiler. They're sort of conceptually fundamental to what it means to type check a Haskell program. And only very recently were they revealed as something that a Haskell user can actually rely on and introduce, which is great. I'm very excited about that. But for now, I'm going to pretend that they're not, because we'll see the constraint solver sort of handles those for you. So I'm gonna in this presentation at least, I'm gonna act like CT is only simple constraints, which in a lot of ways it essentially is. There's also conjunction of constraints. That's another kind of constraint, but in the context of the constraint solver, where we're dealing with sets of constraints, these are sort of trivially decomposed for you into just OR A and show B separately. So really, all your constraint solver plugin needs to worry about is the simple constraints. So I'm going to give you a example here of where an implication tree comes from and how that gets turned into the simple constraints that your constraint solver plugin is going to receive and be expected to handle in some way. So this is a bit of a weird Haskell function just because of the spacing, but it's because I'm going to fill in some details. So hopefully this is consumable just after a few seconds of looking at it. But basically, we're taking an I value that if we know that m is equal to x, if we have a proof of that, then we can return I. Otherwise, we default on empty from monoid for some sort of default response. And here we're relying on the REFL constructor, which carries a coercion, right? So if we know that m is equal to x, then we'll have some evidence, and that's carried in this REFL constructor. And that's what we'll rely on in foo in the just branch. So what I've done here is I've expanded those blanks. I've filled in the blanks. This is now sort of a pigeon language of Haskell and GHC core. In GHC core, we've adopted the implementation method of dictionary passing, where a dictionary is the evidence for the monoid class, or it's the coercion for an equivalence. And basically, in a lot of ways, all the double arrows in your program become single arrows. So a context of type classes is now just a tuple of dictionaries for those type classes. So that's what G1 is here. We now have this G1 argument, which is the dictionary for the monoid. And the memty class method now projects out the empty value inside of whatever instance created this dictionary. And then this triangle is the syntax in GHC core for applying a coercion to cast I from the type X to the type M. And G2 is the coercion. Right? If we look at the signature for REFL, it had a double arrow here, and it carried the equality coercion inside of it. And now, because we're in the dictionary passing pigeon state, this is actually an argument to the constructor, and we're pattern matching on it here. And so this is how GHC, this is how the type checker, the built-in rules of the type checker will handle constraints, right? So when I occurred here, it is declared of type X, and we were using the type M, so it became a constraint where we needed to somehow prove to GHC that I could be used at type M. And so GHC came up with this sim G2 coercion based on the one it had available to it. But this is at the end of type checking, right? This is after the whole constraint solver is done, but we're talking about plugins. So we're concerned about what happens during the constraint solver running or at the very beginning. So I want to back up a little bit. So instead of having the answers here, now we have the questions, the holes, which might not be the best word to use, but for the slides, I'm going to call these holes. So at the beginning of the constraint solver, right? So in the French school method, we type check the program, we type check this program up here, and as a result, we have this sort of implication tree at the bottom. This is the first implication tree I can show you. And this is sort of the way that the constraint solver sees the above program. Right? It's got these constraints that are available to it, G1 and G2, and it's got some constraints that it needs to satisfy, which is W1 and W2. And it's a little hard to recognize the hierarchical structure here because of the bracketing and whatnot. So I've reorganized this as a diagrammatic tree. So this is the same thing. So this G1 is the first argument of the function, and it's in scope for the entirety of the function, including both of the holes. So that's why it's the root of our tree. And this G1 is available for use in the rest of the subtree. And then there's sort of two branches here. We've got a nothing on the left and just on the right. And so in the nothing branch, we only need to find this monoid constraint. In the right, we have some additional evidence because of the pattern match. So this is where the nestedness of the implication tree comes into play, is because of these local constraints made available by gap patterns, or just like a local where binding that also has a signature on it. But I like to think of it in terms of GATs. And then that G2 is only available when we're trying to solve W2. We can't use it over in W1. So this is an implication tree, and this is the basic conceptual structure that the constraint solver is trying to process. And as it's doing so, it will ask your plugin for help. So the first way to think about it is that for each leaf node, the solver is trying to solve that leaf node using all the constraints that are available on the path back to the root. So on the left, we're trying to solve W1 using G1. And on the right, we're trying to solve W2 using G2 and G1. So I've cheated a little bit, and I've created a really simple type checker plugin that just sort of echoes back the constraints it was asked to work with. And in this case, this is a bit of a lie because GHC solves this star function by itself. It doesn't actually use the plugin. But I doctored a little bit so that I would actually see the constraints that were involved from this function. And this is what they look like as if they were being handed to a plugin. And what we're going to see here is we see the G1 and we see the W1 in the first invocation, or in one of the two invocations. And that's a type set level 1 because we're only under 1 for all. And then at type level 2, because we're under 2 for alls, because the for all on the REFL, even though it doesn't bind any type variables, it does bind evidence. So that counts as a level. So at level 2, we have the 2 Gs and a W. So on the left, these little Gs and Ws here, I didn't put up those. Those are part of how GHC pretty prints constraints, because these constraints have a notion of flavor, which is what I'm going to talk about next. And that's how, this flavor is how GHC plugins receive constraints that are part of implications without actually receiving implications. Because there's two different flavor of simple constraint, depending on if it's on the left side of the implication or the right. So that's what this data CT flavor data type is about. So the solver automatically decomposes implications by sort of burrowing into the right side and just collecting the things on the left as givens. And the things on the right become wanteds. So I haven't talked about the structure of CT, but I'm talking about a property of it, which is its flavor, which is a very important concept for understanding plugins. So the given constraints, the ones that we already have evidence for, either it's from the signature of foo, in which case any use case of foo is going to have a dictionary available. So when we're type checking foo, we already have the evidence for the given of the monoid im part, for example. And then a wanted is a constraint where we're trying to find the evidence, right? We have some givens in scope, and using those givens and whatever instances we're aware of, or axioms have been declared, etc., or just special knowledge that your plugin has, you can use all those things together to compose the evidence for that wanted. That's the goal. So that's the primary two types of simple constraints. There's implication constraints, which come from the whole program, but the constraint solver sort of handles those by decomposition so that your plugin will only see a simple constraint. And then depending on which part of an implication those simple constraints came from, they will either be given constraints or wanted constraints. And then your plugin's job is to use the givens to solve the wanteds. So by the semantics of givens and wanteds, we have some rules about how the two are allowed to interact. So you should only use a given to simplify a given. That's sort of saying, I know two things, but together I can interact them to simplify them, to make them more canonical, for example. Or you can use the givens to simplify wanteds. That's sort of the fundamental process. If I use the evidence I have to come up with more evidence for constraints that I need to create the evidence for. And then there's this additional rule, which is that wanted constraints never simplify anything. We don't want to rely on wanted constraints. Theoretically, we could, but the reason we don't is because if something goes wrong in the pipeline, you end up getting a really weird error messages. So because that happened enough, GHC had just decided that we never want to allow wanted to simplify anything. So I'm going to now talk about what I mean by simplify. So what does it mean for one constraint to simplify another? What it means to simplify a given and simplify a wanted are similar but different. To simplify a wanted, you will take, so we'd have some wanted like old whole, which might be the wanted for the monoid im constraint from our foo example. And in order to simplify that, we need to create some new wanteds that are simpler wanteds, and maybe take some of the given dictionaries for the given constraints we have, and somehow combine those evidences, the evidence for the givens and the hypothetical evidence for the new wanteds we're going to make, and then create evidence for the old wanted. Once we do that, we can discharge the old wanted and then just present the new wanteds as our new goals. This is sort of sub-goals in proof theory. For givens, it's the opposite. And this is because givens and wanteds come from different sides of the implication arrow. And the implication arrow has a contravariance to its semantics. So in order to decompose a given, we actually do the opposite. If we want to introduce a new given constraint, we have to explain how we got the new givens constraint from the old givens constraints. So I'll give some concrete examples of both of these now. So here's an example for wanteds. Right? If we have this old wanted, if we want to be able to show a pair of an A and a B, we can simplify that wanted by decomposing it. And we'll decompose it into a wanted of a show A and a show B. Or sorry, a show A wanted. So we're going to decompose the show AB into just show A. And we're doing this by appealing to a given that in this scenario, I'm assuming we have in scope. So we have a given for show B, and we have the type class instance for showing pairs. So given the given for show B and the instance for showing pairs, we can simplify this constraint to now we only need to know how to show an A. So we create a new whole A for show A, and we use that evidence, which we're going to get eventually, to build evidence for the old constraint. And that way we're able to discharge the old one and generate the new one. So we've simplified show AB to just show A. And this is what a plugin is supposed to do with the CTs it receives. So if we received a dict1 of show B that was a given, and we received a dict2 of an old whole that was a show AB, then what we should do is put old whole here, and the evidence we constructed here, and new whole here. We have to use capabilities of the im monad in order to prepare the new constraints and prepare the evidence. But once we have them, then we return those values in these fields in order to tell the constraint solver what we did. So that's how it works for wanteds, except obviously I'm showing you an example here that's familiar to you because you know about show and what GHC can already do. So your plugin wouldn't do this because this is what GHC already knows how to do, but your plugin would do something similar. This is a little trickier for givens because this interface down here, this makes sense for wanteds. It's a little bit weird for givens. So for givens, in order to discharge an old dictionary, right? So suppose we have two givens, no net x and no net x plus y. Those two givens can interact because if I know what x plus y is and I know what x is, then I also know what y is. I can just subtract them. So I can simplify these givens, these pair of givens, to just two simpler givens. I can have no net x and no net y. So I'm going to use old dict 2 to simplify old dict 1 into new dict. And because the contravariance, in order to create a new given, I need to provide evidence for it in terms of the old ones. And this is how we do that. But then the interface is a bit of a mismatch here. I would report the new given here, but you can see there's no place for me to put the evidence. And that's because in the interface for im, if you're creating a new given constraint, you have to provide the evidence immediately. Right? And then I provide the old dict 1, which I'm discharging here, and then there's just a way to sort of fill in a nothing av term here. So this is an example where the interface is enough to work, but it's a little tricky. It's not as polished as it could be. So, but that's the basic idea of you're replacing old, sort of more complicated constraints by newer, simpler constraints, but you have to create evidence in order to do so. But that's what I mean by simplify. You go from an old constraint to a new constraint that is somehow more canonical or more fundamental or closer to being solved. So that's the fundamental role of a plugin. And that's what we generally think of plugins as doing. They receive some wanted constraints, maybe they receive some givens too, and they're supposed to solve the givens or improve the givens using the solve the wanteds or improve the wanteds using the givens. And that's what I call W mode. That's the principal way we think about plugins, and that's where sort of the real work happens. But there's another mode called, I call it G mode, and the only thing you're going to receive is givens. So this is confusing. When you first set out to write a plugin, you'll probably be handled in the wanteds case, and everything will seem fine. And then you notice that your plugin is only being invoked. It's being invoked sometimes with only givens, and you're not sure what you're supposed to do. So I'm going to discuss that a little bit. So W mode is what we sort of expect them to do. It gives you receive wanteds and givens, and you're supposed to simplify the wanteds. It's okay if you don't solve all the givens or solve all the wanteds because those will become the inferred context, if that's possible, or it'll be a type error, which will be appropriate. In G mode, it's a little more mysterious. As far as we can tell, the only necessary reason for G mode to exist is to identify unreachable code. So if your plugin knows something about equalities, right? Like let's say it knows about, actually, I don't know if GHC knows this or not, but let's say it knows you have a constraint that x is greater than y, and you have another constraint that y is greater than x. So obviously those two are a contradiction. GHC might know this already, I'm not sure, but presuming it doesn't, if your compiler plugin knows about that contradiction, then any sort of branch of code that introduces gap patterns that together introduce these two constraints would be an unreachable path, assuming all the other code is not buggy. And so really GHC's exhaustiveness checker should consider those patterns unnecessary. Because if it doesn't, then you're in this sort of catch-22 where if you write those patterns, then GHC will consider them ill-typed. You'll get a type checker error. But if you leave those patterns out, then GHC will consider the case expression to be incomplete. So either way you go, you're getting either a warning or an error. Even though your plugin is able to see the contradiction, but that's because of a bug in GHC right now. So eventually GHC's pattern checker will use your plugins, in which case it works out very nicely in that your plugin identifies the contradiction, and so the user can just leave out that impossible case, and this is what we want when we're using very smart types. That is the fundamental purpose of the G mode as far as we know. There's a couple other things you can do with it, but they're not really crucial. You can do those things during wanted mode. So feel free to ignore G mode when you're starting out with a plugin, But be aware that it will eventually be important unless you know your plugin will never do anything about identifying reachable code. So you might want to think about how to add it ahead of time, because adding it after the fact might be a little difficult. Okay, so I've talked about wanteds and I've talked about givens. Those are the two primary constraints. And I've talked about the ways in which GHC invokes your plugin in terms of wanteds and givens. The last bit, so that was the end of the sort of simple section. That was the 0 to 15% of your first initial effort. The next step I'm going to talk about are the other flavors of constraints. So givens and wanteds make sense in terms of this tree, implication tree, but there are two other kinds of constraints, and they just seem like a mystery. And for the most part, your plugin will do plenty fine without supporting them. And then one day you'll find a kind of fancy GHC program that's using your plugin, and it will fail. And you'll see that, oh, there's a derived constraint, and I don't support those because I don't know what they are. And then you'll want to know what derived constraints are. So hopefully this slide will help you at that point. So a derived is just a special wanted in that it doesn't need evidence. If you want sort of a conceptual background on what the purpose of a derived is, there's a paper by Mark Jones, actually several papers. He did a lot of work on qualified types back at 25 years ago. But the notion here is for improvement. And what this is basically it's a set of constraints where we don't actually need the evidence. But if we know that those constraints must hold, then we can do better. We can do a better job of unification. We can unify more type variables. And I see I'm running over time, so I'm going to go a lot faster all of a sudden. But what derives do are they enable more unification, and that unification might then let us do a better job simplifying the wanteds. So it's sort of an indirect way to do a better job of solving constraints. The key difference here is that derives are allowed to solve simplify derives. Wanteds can't touch wanteds, but a derived with no evidence is allowed to simplify another derived with no evidence, because you might be able to find, ultimately, you might be able to find an equivalence, which then becomes unification, and then that unification lets you make better progress on the real constraints. Yeah, I'll skip that for now. So there's one additional flavor, which is an optimization involving a wanted and a derived. So this is all four flavors. And the given and the wanted are the primary two. We've got this derived, which is sort of like a shell of a wanted. And then we've got a WD, which is an optimization. Instead of carrying a wanted and a derived for every constraint, right, every wanted could also be a derived. And they start off that way. They start off as a WD. And it's just an optimization so that we don't maintain two constraints which are the same. Because if I use a given to simplify a WD, that's just one piece of work instead of using the given to simplify the W and the D at the same time. So a WD is just a pair represented in a compact way to save work of a wanted and a derived. And eventually, there may reach a point where you have a derived in scope that can simplify the derived part of the WD. It can't simplify the WD because the WD is also representing a wanted, and Ds can't simplify Ws. So at that point, GHC built-in rules do this, and eventually your plugin will need to as well. It is time to split the W into a W and a D. So there's going to be functions in the interface to do that. But you need to recognize when it's necessary. You need to split it, and then you can simplify the D separately. So all told, we have these flavors, these four flavors, and they interact in the following way. Gs can simplify anything. That's sort of their main purpose. Wanteds can't simplify anything. That's the rule we saw. And then the Ds and WDs can interact with each other. Because the fact that they have no evidence and they just sort of explore all necessary truths, they're a little, we can have them interact a little more aggressively, but you just have to remember to do the splitting of the WDs when appropriate. With that matrix of interactions that are allowed, we have this pipeline. I just sort of came up with this on my plugin recently, and I'm trying it out, and it seems very promising. But it's sort of a simple plugin that lets me deal with things sort of one at a time, and I maintain this rule that I'm not using a constraint to simplify other constraints until that constraint is as simple as it can be, right? So we use the Gs to simplify each other, and then we know all the Gs are simple, are totally simplified, and then we use the totally simplified Gs to simplify everything else. And then once we have totally simplified the Ds and the WDs, which are just Ds, right? Then we can use the Ds to simplify other Ds, and now all the Ds are as simple as they can be, and then we can use them to simplify the WDs, and then we're basically done at that point. Again, like I said, for the most part, you can just do these first two when you start out writing a plugin, but eventually you will need to support the Ds, but you can get quite a ways with just Gs and Ws. The question of when do you need support Ds is most easily answered by when your new test case that's somewhat more complicated than your rest starts to fail. But I anticipate that will happen from these features because these are the only features I'm aware of that actually use derives. Functional dependency is a big one. If we have these two constraints, because of the functional dependency on monad reader, this is the same monad, and so I know it has the same environment. So I have a derived equality that A equals B. So that's a derived constraint. And your plugin might need to recognize that. So if it was a different class, if it was a different class, then A and B might be naturals. And maybe my plugin knows that those two naturals are equivalent, whereas GHC doesn't. Right? So that's a derived equality that my plugin would be able to simplify and should in order for whatever other constraints are in scope to benefit from the fact that we in fact know that A and B are equivalent. So similar logic for implicit parameters. Maybe these star types have arguments that include naturals. And so your natural plugin would have to reason about those arguments. And then plugins. So oftentimes when my plugin realizes two types should be equivalent, the easiest thing for me to do is to actually just emit a derived equivalence and let GHC's built-in rules decompose that equivalence and break it down and do all the necessary unifications. The other thing I thought might create derives is injective type families, but I don't think it does. I think if F is injective and we know that these two are equivalent, then because it's injective, we can conclude that A and B are equivalent. And that doesn't involve a derive. That would we just decompose this equality constraint into a simpler equality constraint of A equals B. The caveat is that there are reasons that GHC doesn't actually do that right now. So see this GHC ticket on GitLab. But this is a candidate. Maybe a plugin might want to see if that's a safe thing to do. So a plugin could add that functionality to GHC. That might be a fun place for somebody to start. There might be others. I don't know. I'm not an expert. I've just been working on this I have a hobby project plugin that I've been working on for probably 3 years total at this point, on and off as work permits. So there's gaps in my knowledge, but a lot of it has been hard won, and I'm hoping I've conveyed a good amount of that to you today. So these are the bits we talked about. We talked about simple and implication constraints, and implication tree, which is how these arrives from a Haskell program. Why GHC invokes your plugin, and when, in terms of G mode and W mode, and the different nodes in the implication tree are where it tries to chew on constraints and asks for your plugin's help. The 4 different flavors of constraints and the ways in which they're allowed to interact, and so the suggested stages of your pipeline in order to respect those constraints. The next thing for me to talk about, if I had asked for an hour instead of a half hour, would have been the structure of CT. So I just talked about the flavors of different CTs, but the CTs themselves, beyond their flavor, have different structures. In order to talk about that, you really need to understand a lot more of the details of the built-in rules of GHC, and particularly how it reasons about type family equalities. So that's a lot more work. It's quite sophisticated. It's fascinating. The outside-in paper talks about it. The outside-in paper introduces the outside-in algorithm, but it also introduces the built-in rules X, and they explain why the CT data type has the type it does, or has the structure it does. You're also going to know how to build evidence. Usually at the start, you can get by with the existing documentation, but hopefully the project we have at ZeroHack will eventually lead to a place where we talk through all these things. And if you'd like to help, please come by the TC Plugins channel. I didn't really include references in my slide because there's a huge list of references, which is where I learned everything I've ever learned. And I just put it on this markdown file on the repo. So thank you for your time. Sorry I went along a little long. Hopefully it was helpful. And please let me know if you have any questions. Thank you.
Thanks a lot for the great talk. Yeah, we have had a couple of questions. I know we went over time, but if it's all right for you, we can go through a few of them.
I'm fine. I'm sorry for inconveniencing anyone if they had to go, but I'm good to stick around.
Awesome. So I've tried to keep track of the slide numbers as well for context.
Thank you.
So on slide 11, I think There was the question if implication is what is introduced by quantified constraints.
Yes, yeah, that's the recent development. Sorry, I should have said that. That's the recent development that lets Haskell users write implication constraints explicitly. The GHC solver basically already knows how to handle them, and it always has, but there was a good amount of research they had to figure out in order to allow users to write them. I don't understand how that works. The paper was nice, but I didn't take the time to fully understand it. But there's a nice paper that explains that.
Cool, thank you. On, I think it was slide 16, the question came up of how does GHC determine which constraints to name whole?
Yeah, I think holes are, those are coercions that it's trying to find. Right. So in the first example here, this is the name of the evidence of the given constraint. And this is the name of what will be the evidence of the wanted constraint. And you'll see that the name of a given equality is co for coercion, and the name of a given, or the name of a wanted equality is whole of co. I'm not sure if there's a more interesting distinction going on here, but in my experience, it just calls wanted coercions holes. This might be related to the typed holes work. Again, I'm not sure. My plugin hasn't dealt with typed holes, so I don't know if that's connected, but it could be. I don't know why the wanted dictionary isn't called a hole.
Another question was, I think, around slide 20. And the question was, what happens when there are multiple potential ways of simplifying a constraint?
Yeah. So GHC, and this is discussed. This is discussed in the outside-in algorithm paper at the 2016 JFP. They talk about this notion of having a guess-free solver. In that, if there are multiple ways and none is obviously better than the other, then it does nothing. This is related to why if you write a Haskell function that uses gap patterns, but you don't provide a signature, then you'll get this error message about untouchables, or maybe rigid. I don't remember what it's called nowadays. But that's similar. GHC doesn't have enough information to figure out what is what, and it refuses to guess because the guess might be wrong. So if there are multiple ways to solve a constraint and they're not, and they are distinguishable, then I believe the right thing to do is to not do anything. That's my understanding at the moment. If the two paths are equivalent, then I think you can go ahead and just pick whichever one is convenient. But there are subtleties there. You have to be very confident that the two paths are equivalent. So for example, it's possible for GHC right now, if you have an ORD A constraint in scope, and then you pattern match on a gap that brings another ORD A constraint in scope, conceptually those two, it shouldn't matter what you choose. But because, again, I haven't really looked into the deals here, but I know that it matters which of those you choose. I think you're supposed to use the innermost one. I don't remember. But I think this has something to do with overlapping constraints and maybe existentials. So it can be subtle. When it appears like it wouldn't matter, it might matter. So be very careful in those situations. But that's unfortunately the best abstract advice I have to give for that question.
Thank you. And I think it was in the context of the next slide. The question was, is it allowed and is it ever useful to return discharged constraints which weren't provided as arguments to the plugin?
I don't think it's allowed. I've never tried it. The wiki page that Adam Gundry wrote years ago says that these CTs must match one of the given CTs. Sorry, one of the CTs. So this CT must be one of the ones the plugin was provided. I don't know what would happen if it weren't, and I don't know what could be useful if it. Oh, I suppose it could be useful if your plugin logic was sort of incremental. Like if you were generating CTs in a loop inside of your plugin, and then you realized you could simplify those CTs before you ever returned to GHC's constraint solver. Yeah, I think that's where I maybe wanted to do that before. And ultimately, I decided against it. It seems inefficient, but for now, in my development of a plugin, my general rule is as soon as I see something that can change, I yield it back to GHC. So hopefully the built-in solver can, make progress and maybe simplify things even more. So the next time I'm invoked, it's better. Or the next time it's invoked, I have even simpler constraints to work with. But really, it's because I didn't want to write my own loop that managed constraints and incrementally solved them sort of without being able to rely on GHC to pipe the evidence around. And it might be because I wasn't able to return those intermediate constraints here in order to assign the evidence to them. So my rambly advice is to avoid that. And for now, if it's possible, just yield to GHC as soon as you can.
Cool. Thanks. I think that leads directly into the next question, which is, what's the right strategy for plugins? Try to do as much as possible in one iteration, or try to do as small steps as possible to enable interaction with built-in rules and potentially other plugins?
Yeah. Great point about other plugins. That would be my advice, is right now take as small steps as possible. That will probably also make it easier for you to debug when something's going wrong. There's a lot of output when you enable the various dump, trace, TC warning flags to get GHC to show you what it's doing. I think the only caveat to the advice of to take as small steps as possible is you want to recognize contradictions as early as possible. And ideally, those contradictions would report the constraints that the user would recognize, as opposed to the constraints that you have so far incrementally created until you recognize the contradiction. And there's only so much you can do there. And I guess for now, I consider that sort of a secondary concern because it's only relevant for a ill-typed program, in which case, it's just a matter of how useful the error message is. And generally, they're going to be pretty hard to work with anyway. Until, right, you've put in 95% of the effort and you're climbing that last final hill, which is to make your plugin as useful as possible for the user, at which point you might start, worrying about identifying contradictions, for example, as early as possible. But other than that, in my experience, it makes it easier on my plugin logic. It's simpler, and it's easier to debug if I report my changes as soon as possible.
Thank you. And another question was, and I think a comment pointed to the glossary that you had on the last slide. Is there a list of typechecker plugins that exist somewhere?
Yeah, there's a couple lists. I have one in this file. And Matthew Pickering also has a really nice page where he collects basically all sorts of references and examples of all kinds of plugins, not just typechecker plugins, but also core plugins and source plugins and front-end plugins. Are those the same thing? I'm not sure. And I think I have his page listed in this file as well. I think if you search for the keyword catalog or just Pickering, it'll lead you to his link there. I think maybe there's 10 or 20 total. In the wild. So there's not a lot, and some of them are more sophisticated than others, but they're all, for the most part, they're all doing different things, and it's all really interesting.
Cool. Another question was around slide 29. When you emit a derived to say that two types are the same, do they have to be type variables?
No, and that's the big benefit of just emitting the derived, is because GHC, if the derived equates two types that are involved, then GHC's built-in solver will decompose that equality as far as it can until it does get to something involving a type variable. So instead of your plugin needing to, for some reason, do that decomposition, which is essentially unification, you can offload that work to GHC. That might be another reason that I suggest to yield the GHC as soon as possible. Let's see. I think the only risk that I recall with deriving those equalities is GHC might not. It might ignore the equality, because certain equalities are only allowed according to rules that I did not discuss here. So there's things like an occurs check, or different levels on variables. I didn't get into it, but I did put the word on here because it will be relevant to you eventually. These different levels are tagged on the type variables. And this is related to type checking equalities in the presence of local equalities. So this is why, this is how GHC knows to refuse to infer a type for a function that involves GATs with equality constructors in a particular way, is it does it according to these levels. This example doesn't really exercise it, but this notion of level is crucial, particularly in the equality solver. And if the levels of the type variables in the equality you omit are off, then GHC might just refuse to do anything with that equality. And that's not really a risk unless your plugin assumed that it would. And one way you could assume that it would is if you omit the derived equality and then GHC doesn't do anything with it, then you will be given the same constraints again. And your plugin might conclude to omit the derived equality again. And then you're stuck in a loop. So that's the main caveat I have for that piece of advice about just omitting equalities and assuming GHC will do the hard work. Is before you do that, you might need to check whether GHC will handle that equality or not. Otherwise, you might find yourself stuck in the loop.
Cool, thank you. And yeah, looking at the time, maybe let's make this next one the last question. Question was, which plugin are you working on yourself?
Yeah, thanks. Fun question. My hobby project has always been to get something along the lines of row polymorphism, and that's mutated over the years. It started off as coxswain, which I think got some attention back in the day, but coxswain was really me just like flailing my arms trying to figure out what a constraint solver can do. And I've iterated on it a few times. So I have one currently going. I don't know if it's listed in the biblio because it's not ready. I guess I'm a perfectionist, clearly. But it's something along the lines of linear combinations. So you can have a kind that's inhabited by linear combinations where the coefficients are rationals, and the solver knows about equalities based on just sort of addition of coefficients. So this is a sort of a group theoretic object that is most comparable to a multiset that has signed multiplicities that are rationals, which is very general. It's very similar to what Adam Gundry's plugin was for the units of measure plugin, and a multiset where each element is a unit or a dimension, and each multiplicity is the power of that unit or dimension in the unit of the quantity. You'd like meters over second to be the same as meters times inverse seconds, or meters times seconds to be the same as seconds times meters. So those are the kind of equalities that this would let you handle. And Adam Gundry's plugin does, but I'm trying to make it a little more general with the rationals, which is just a choice. But also, I think with that same machinery, we'll be able to do something comparable to whatever the set analogy of a map is. So row polymorphisms provides a map at the type level. And I think basically if you constrain the rows of the fields, the field names of the rows to be the same as their image. So it's like a set. You can say what fields are present instead of this field maps to that and that field maps to that. So if it's just whether or not the field is present, I think you can squeeze the same functionality out of this signed multiset rational thing. So hopefully more on that front as I get to it, but 40 hours a week of a real job makes my progress here bursty. Thanks for asking. Fun question. I'll put the link in the biblio MD file at some point.
Thanks a lot. It sounds like a fun project.
Yeah, it could be really cool if it works.
All right. Thanks a lot for the great talk. And Thank you, everyone, for the great discussion and the questions. Let's move the rest of the discussion and questions to Discord. And this concludes the GHC track for this year's Zuri Hack. So thank you, everyone, for joining, and big thank you to all the speakers. And enjoy the rest of Zuri Hack. See you around. Bye.